All right, anybody have any questions from last time or on practice problems or anything? Yeah.
Could you please go over this section? I think it was problem number 9, where it had all of like the millimeters or, you know.
Yeah, number 9.
Yeah, that was. I was just confused why they did on the salt solutions.
Okay, so number 9. So in scientific notation, express 15.5 kilometers using meters, millimeters, that stuff. Okay, so that has to do with those prefixes. So let's see. Number 9. Express 15.5 kilometers in meters, millimeters, microns, which is micrometers, miles, megameters, which I've never heard anyone say, and centimeters. Oh, that's huge. Okay, so 15.5 kilometers is the starting quantity, and I am going to just right away. So we're starting with 15.5 kilometers. I'm going to replace that kilo with times 10 to the third. So I'm going to start with, so A, 15.5 times 10 to the third meters. And that's the answer, although that's sort of, that's not really scientific notation. So to make it scientific notation, this would be 1.55 times 10 to the fourth meters. All right. Any questions about that first one? So I just replaced the kilo with times 10 to the third. You can think of those two things as meaning the same thing. Yeah?
Yeah, I think if you're more visual, you can do it like you're doing a dimensional analysis. You can do 1,000 on the top and just 1 on the
Yes,
bottom.
you can. Yep.
And so just multiply your answer by 1,000.
Yes.
Okay.
And then B, express it in millimeters. So I'm going to start with this same thing again. So 1.55 times 10 to the fourth meters. And 1 millimeter is equal to 1 times 10 to the minus third meters, because milli means times 10 to the minus third. And so you get 1.55 times 10 to the, oh no, you don't. Yeah, 1.55 times 10 to the seventh millimeters. Anyone have any questions about that one? So you can always, so these prefix things you can use two different ways. And sometimes you have to do one, sometimes you have to do the other one. First, you can just replace the prefix with its alternate meaning, times 10 to the whatever. And the second way is you can recognize that if kilo means times 10 to the third, for example, then 1 kilo whatever is equal to 1 times 10 to the third whatever. And then based on this, you can do the ratios and do that and do it the way we do unit conversions.
Can you explain how you got to a positive 7?
Yeah, so one thing you can do is just plug it into your calculator and it'll do that for you. Your calculator has scientific notation on it, most likely, but the exponent rules say if you're multiplying, okay, so two things. 10 to the m times 10 to the n is equal to 10 to the m plus n. And 1 over 10 to the n is 10 to the minus n. So in this case, 10 to the fourth divided by 10 to the minus third is the same thing as 10 to the fourth times 10 to the positive third because of this division definition. And then that's equal to 10 to the 4 plus 3, which is 10 to the 7. But you don't really have to. I mean, that's sort of a nice couple of tricks to know, but if just plug it into your calculator and it'll do it, and that's that. And then part C, going to micrometers. So we're starting out with 1.55 times 10 to the fourth meters. And 1 micrometer, people call that a micron, but think of it, you can think of it as a micrometer, is 1 times 10 to the minus 6 meters. And so this is equal to 1.55 times 10 to the fourth times 10 to the positive sixth, which is 1.55 times 10 to the 10 microns. Miles, I can't remember, on the back of that handout, oh, I have it right here. It gives you some conversions, so I'm just going to use the conversions that are given. So we have a conversion from miles to feet and from feet to meters. So I'm going to have to do it in a couple of steps. So 1.55 times 10 to the fourth meters. One meter is 3.281 feet. So now we've converted from meters to feet, and then 5,280 feet is 1 mile. And I don't know what you get there, but could someone calculate that? Yep. With the slashes and stuff? Yeah, so every one of those slashes, think of that as just the boundaries of the parentheses. So that's just a slightly faster way of writing 1.55 times 10 to the 4th meters times 3.281 feet over 1 meter times 1 mile over 5280 feet. Look at all that time we saved. Yeah, I think they do it like that in chemistry a lot. I don't know. That's where I picked it up. Did anyone do that calculation that I demanded that you do? 9.63 miles. How many more are there? Okay, I'm going to skip those two. But it's the same idea as B and C. Just using, so like for part E, we're going to use the conversion factor that 1 megameter over 1 times 10 to the 6th meters is equal to 1, and use that as the conversion factor, or the multiply by that to convert. Any other assignment problems that you'd like to see? Tessa? No. Okay. If Tessa can't do it, the rest of you definitely can't do it.
Do you have a room yet for Monday?
For office hours?
For like the Monday tutoring?
Yes. Yeah, thanks. So every Monday from 3 to 6, these are like my office hours. And Wednesday from 5 to 6 are going to be 2 doors down here in S1324. Oh, where our lab is. Okay, where lab meets. That's where I'm going to do office hours. And then the Tuesday office hours from 1 to 2 I'm going to do in my office. So that's S2302 because that room just isn't open at that time. Any other questions?
Sorry, was it Tuesday or Thursday?
This is Tuesday, and then Monday and Wednesday. Yep. All right, if you don't say something, you're going to have to learn something new. Okay. So moving on to really everything we've done so far is sort of general science related stuff that's useful in any kind of science class. So we're going into our first physics topic, and that is kinematics of a particle along a line. And the meaning of these things is, first, kinematics is just describing motion, not talking about the causes of motion yet. So describing motion, but no causes. We're not talking about forces or masses yet. We're just talking about things that you could figure out from watching a careful video of something. Okay? So it's just describing the motion, relationships between different ways of describing motion. A particle is it doesn't have to be a tiny object, but treating something like a particle just means that we're treating it as if it has no length dimensions. We're treating it like it has no length at all. Like it has no length dimensions. And because of that, we don't care at all about the orientation of the objects. We only care about how their location changes. So no orientations. And it really, what you treat as a particle is, and what you don't treat as a particle has to do with whether you care about the orientations or not. You know, planets are very big things, stars are very big things, but in a lot of astronomical calculations, you treat them like particles because you just don't care whether the planet has the spot side up or the spot side down. You just want to know where the center of the planet is. And so it's not really so often things that are very, very small are treated as particles, but you can treat things of any size as a particle if you don't care whether it's right side up or upside down, you know. And then along a line, well, that's pretty self-explanatory, but one thing that means to us is that at any instant, the object can only go in two directions. It can only go forward along the line or back along the line. Later, when we get into more complicated stuff, where stuff is moving in a plane, then it's going to have all these choices. You know, if the plane is like the plane of the screen, like a bug moving on the screen would be motion in a plane. And if the bug's here, it can go that way or that way or that way or that way. You know, has all these choices. But if it's confined to moving along this line, it can only go this way or that way. Okay, and that's going to make the math a lot simpler. The variables, or the, let's say the physical quantities that we're going to deal with for kinematics of a particle are position, and related to position is displacement, then velocity, acceleration, and time. Okay, so all of the kinematic calculations we're going to do involve position, displacement, velocity, acceleration, and time. A lot of these are similar to quantities that we're used to talking about in everyday speech, but they're a little bit different. And the way that they're different is position and displacement. Everything except time. So position and displacement, velocity and acceleration all contain directional information. And so I want to make a comparison between these quantities that we're going to use in physics that have directional information and the quantities that we're more used to talking about that don't. So these quantities are similar to quantities we use in speech. That don't contain directional information. Okay, so here's a little table comparing the directional quantities, which are the ones that are going to be important to us, and non-directional quantities that we're more used to. So the first directional quantity that I mentioned is position. And we're going to use that idea of position to define the quantity displacement. The non-directional version of displacement, quite similar to it, is distance. So distance and displacement are the same thing, except sort of the same idea, except displacement tells you something about direction too. The second one is velocity. That's a directional quantity. The non-directional quantity that's similar to velocity is speed. And the third one is acceleration. That's directional. This one, in some ways, is even more confusing because we actually use the word acceleration, but in everyday speech we use it to mean something a little bit different. We talk about acceleration if something's speeding up, and deceleration if something's speeding down, slowing down. Deceleration. Okay. So, like when you, if you drive to Duluth and then you drive to Des Moines, you know, it's however far, 200 miles in either case. Those are in two different directions, but the distance is the same in both cases. Displacement, if you talk about the displacement when you went to Duluth versus going to Des Moines, you'd get different answers for that because they're in different directions. Same thing with speed. You know, if you're going 55 miles an hour north, that's the same speed as going 15 miles per hour south. Acceleration and deceleration, no matter what direction you're moving, if you're speeding up, you talk about accelerating. If you're slowing down, you talk about decelerating. Okay. With the directional quantities, so this is an important thing to associate with these. Along a line, the direction is given by the sign. And the reason that the sign can be used to give a direction when you're talking about motion along a line is because when you're moving along a line, at any instant you only have two choices of the way to go. And sign has two different properties. So you have to choose in every case before you can come up with meaningful numbers. You have to choose what's going to be your positive direction and what's going to be your negative direction. But once you choose those, a positive answer for displacement means this way, a negative answer for displacement means that way, and so on. Okay, so anytime you see a sign when you're talking about kinematics along a line, that sign is what's giving you the directional information. Okay, so the first stuff I'm going to talk about is position. And displacement. And distance. Distance isn't going to be very useful to us, but I am going to talk about that. And all of these values have units of length. So the SI units for position, displacement, and distance are meters. So for the position, you can think of position as a number describing the object's location. The position can only be determined once two things are specified. And those are, first, a location corresponding to 0 position. And 2, a direction corresponding to positive. Okay, so let me draw a picture of how this works. So there's the line, and let's say you have a train moving along the line, because I learned how to draw a train once. In like 1804. One thing I know is trains have those cow catcher things. And in order to treat this train as a particle, we have to choose a point to represent its location by, right? A particle is an object that we're treating like it acts at a single point. And so I'm going to choose the center of mass of the train. That's this symbol. Did you know that this symbol represents center of mass? You know, like in commercials, like car commercials, when they have the crash test dummies, and they have this symbol all over their body. The reason they have that is that the center of mass of an object is an important thing for doing detailed physics. And so a real crash test dummy has a center of mass marker on each part of their body, so that when they watch the video in slow motion, they can use the locations of the center of mass to do the physics and figure out what the forces are at the joints and all that kind of stuff. So anyways, that's what we're going to treat as the location of the train. And the idea that I was getting at here, so what's the position of this train? Well, there's, what? Well, the idea is there's no answer to that until it could be anything, but there's no answer to that until we specify a location that we're going to call 0 and a direction that we're going to call positive. Okay, so now I'll say, let's make this our 0 position. It's arbitrary. And let's say this is our positive direction. And then let's count back meters from there. Should have made my meters bigger. How many was that? 15? 13. Okay, so now that we've chosen those, if each one of those is a meter, we can say that the position of the train is negative 13 meters. Okay. And you can see how that sign works to give a direction for that position. If the train had been on the other side of the 0, you know, we would have called it positive something. The fact that it's negative said that it's, you know, if this is the positive direction, that the train is located in the negative direction from what we're calling 0. And if you can give an object's position you can show it on a number line. That's something that's going to be useful for us. So for this train, well, since it's moving along a line, it almost is already on a number line, but if you have positive that way, and your 0 here, here's negative 13, and that's the location of the train. One thing that we're going to use all the time is a relationship between the position of an object and a certain instant in time. And thinking sort of similarly, we can't specify a time that corresponds to a physical instant until we choose a 0 time to relate that to. You know, like think about this train. You know, we haven't chosen a 0 time. So what's the time corresponding to this instant? Well, it's 2 hours after noon, and it's, you know, 1 billion years after the formation of the Earth or whatever. We have infinitely many choices until we say we're going to reference the time at this instant to some specific other instant. So to associate that position with a numeric time, we have to choose an instant corresponding to 0 time. For example, say that we had chosen our 0 time to be 8 seconds before this location, this instant that's drawn, okay? So say we chose 0 time 8 seconds before the instant shown. then we can say the position at time equals 8 seconds is negative 13 meters. And mathematically, the way that we can say that is we can treat position as a function of time. And then we can write that the position at time 8 seconds is equal to negative 13 meters. And what's your favorite thing to do with functions? Someone said graph them, right? No? Well, anyways, if you would have said that, I would say yes. You can plot position and time on a position versus time graph. So I'll call it P versus T graph. We're always going to do it with position on the vertical axis and time on the horizontal axis. And so what we just established, I don't know why I made that number so big, but now I got to go down to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. At the instant that I showed in that picture, the location of the train is negative 13. And the time is 8. 1, 2, 3, 4, 5, 6, 7, 8. And so this point on the graph indicates the position and the time at that instant shown. Okay? And if you know the time at every instant, if you know the position at every instant, you can, instead of just plotting a single point, you can plot the whole function that represents the object's position as time goes by. Okay? And just like in math classes, you've done a lot of math based on functions, how the independent and dependent variable relate to each other with functions. We're going to do the same things with position and time. In here? So before you can plot a position versus time graph, so the existence of a position versus time graph requires that you've chosen those three things. So the fact that I plotted these at all implies that we've already chosen a zero position, a positive direction, and a zero time. Okay. So if you ever are given just a curve like this, it means those choices have already been made, and you have to use their choices, the problem's choices. One thing to notice, to keep in mind, is mathematically there's no reason that we couldn't call things negative time, but people just don't ever do that. So just to communicate with other people doing physics, we'll never use negative times. It's not that you couldn't, you could do the math just the same, but we won't. So the 0 position that gets chosen always has to be before whatever events you're considering. All right, so now with this idea of position, we can talk about displacement. And I'll also bring up distance. If you specify 2 different times, I'll say the first one is called TI for T initial, you know, the initial time. And TF is the final time. The displacement from TI to TF is the position at time final. So position at TF minus the position at T initial. So for example, let's say an object's motion is represented by this position versus time graph. There's 1 meter, 2 meters, and then -1 there. And 1 second, 2 seconds, 3 seconds. And let's say that the object's motion goes from 1, so when time is equal to 0, the object is at location 1. At time equals 1 second, the object is at location 2 meters. At time 2 seconds, the object is at location -1. And then finally at time equals 3 seconds, the object is at position 0. And so the whole motion could be something like that. And we want to figure out what's the displacement from part A. Let's go from 1 second to 3 seconds. And then second, from 2 seconds to 3 seconds. Okay, so for part A, based on this curve, we know that the displacement is going to be the position at 3 seconds minus the position at 1 second. Based on this graph, what's the position at 3 seconds? Yep. So that's 0 is the position at 3 seconds. Just go across to 3 seconds and the height is the position. And what's the position at 1 second? Yep. That's 2 meters. And so the displacement is equal to negative 2 meters. The negative means in that time interval that overall the object moved in the negative direction. So now we want to do the same thing from 2 seconds to 3 seconds. So this time the displacement is the position at 3 seconds minus the position at 2 seconds. What's the position at 3 seconds? 0 again. What's the position at 2 seconds? Negative 1, so we're going to do minus negative 1 meter. And so this time, we have positive 1 meter as the displacement. So from 2 seconds to 3 seconds, the object overall moved in the positive direction. One thing to notice about displacement is no matter what the object does in between these two instants, if the object makes a round trip, the displacement is going to be 0. So if the object finishes where it started, the displacement is 0. So like a 10,000 meter track race is 25 laps around a track. What's the displacement? 0. So don't get all, don't be all proud. Your displacement was 0. Okay, so now what about distance? How does this relate to distance? To figure out the distance traveled between two, so to figure out the distance traveled from a time t initial to a time t final, plot the motion on a number line. And so with the example that I have here, So let's say we're going to calculate what's the distance traveled from time equals 0 to time equals 3 seconds, and then second from time equals 1 second to time equals 2 seconds. Okay, so for part A, I'm going to plot that motion on a number line. So there's the 0 position. This is the positive direction. On a number line, this object goes from position 1 to position 2. So I'll plot that first. So that's 0, that's positive 1, positive 2, negative 1. And we know that it starts out by going from 1 to 2. Then the next thing it does is go from 2 to negative 1. So you can think of like the next leg of the journey is from 2 to negative 1. And then the last leg of the journey goes from negative 1 to 0. And now we're just going to add up the lengths of these legs. We don't care about direction anymore. And so what's the length of the red leg? So yeah. So the distance is from 1 to 2. That stretch has a length of 1. From 2 to negative 1, what's the length of that green arrow? 3. And then what's the length of the blue arrow? 1. And so the total distance traveled is 5 meters.
So are we just using 5 meters because it's the SI, or is it going to be like specified?
It'll be specified. Maybe I'm being a little sloppy, but yeah, I'm just assuming that it was specified that those are meters. Okay, so
About the displacement.
what?
But if you're talking about the displacement, then wouldn't it be like negative 1?
Yes, the displacement would be negative 1. That's exactly right. Yep. And then for the second one, we're going to do the same thing, but we're just not looking at the same amount of time. So here's the number line. And now we're just tracking the motion of this object from time equals 1 to time equals 2. So when time equals 1, it starts out at positive 2. And at time equals 2, it ends up at position negative 1. And that's the end of the interval we're looking at. So what's the distance traveled here? Just the length of this arrow, so it's just 1, 2, 3. Any questions about that? Okay. This is an example problem that's sort of similar to some stuff that's in the practice problems. So let's say that this is the lake. And here's the shore. And here's you. Ooh, nice butt. Okay, looking out over the sea. Here's a buoy, and here's a raft. And we'll say that the distance from the shore to the buoy is 20 meters, and the distance from the buoy to the raft is 15 meters. And we'll say the swimmer goes from the shore to the buoy. No, let's skip the buoy. Goes from the shore to the raft. In 60 seconds. Then goes from the raft to the buoy in 20 seconds. And then decides to go back to the raft, and so goes from the buoy back to the raft in 30 more seconds. And what we want to do is plot a position versus time graph we want to do it two different ways. The first time we're going to do it with the 0 position on the shore. And the positive direction out toward the water. And then for part B, we want to choose the 0 position at the buoy. And the positive direction toward the shore. And the way to approach problems like this is, first we're just going to do a simple diagram of what the motion looks like. So I'm just going to make a point that represents the shore. A point that represents the buoy, and a point that represents the raft. Oh, and I skipped one thing. For both of these, let's say 0 time is when the swimmer starts swimming. Okay, so no matter what the zero position is or the positive direction is, that doesn't affect the swimmer. The thing that you're observing is totally independent of your choices of positive direction, zero position, zero time, right? The person isn't even aware that we're there. That's sort of creepy. Okay, so the first thing the swimmer does is this. Starts out at the shore, goes to the raft. The next thing is this. And then the last thing is from the buoy to the raft. So now that we've symbolically, shown what the motion looks like, now we can go to this same thing and start to define what these positions are numerically. So for part A, where's the zero position chosen? The shore. So the shore here is the origin, the zero position. And the positive direction is to the right. And so now if it's 20 meters from the shore to the buoy, what's the numeric value of the buoy? So we're going 20 meters in the positive direction from 0. So this is 20 meters. And now we're going another 15 meters in the positive direction from the 20 to get to the raft. So what's the numeric value at the raft? Yeah, positive 35. And so what this says is the swimmer starts at 0, swims to 35 in 60 seconds, back to 20 in 20 more seconds, and then back to 35 in 30 more seconds. So to plot this on a position versus time graph, the times that matter are, so there's 60 seconds, there is another 20 seconds. So what's the numeric label for the time 20 seconds after 60 seconds? Yep, 80. And then 30 more seconds? Yeah, 110. And now we can just read the position values off of this drawing. At 0 time, the swimmer is at position 0. At 60 seconds, let me write these numeric values on here. So there's 20. There's 35. At 60 seconds, the swimmer's at 35. At 80 seconds, the swimmer's at 20. And at 110 seconds, the swimmer's back at 35. So it looks something like that. Any questions about that thought process? Now we're going to do the same thing, follow the same steps, but we just have different values and a different positive direction. So for part B, I'm going to take this. You have to draw it again like a sucker. Okay, so that still describes the motion, right? But now everything's going to be labeled differently. So the second one, the 0 position is chosen at the buoy. So now the buoy is labeled 0. And the positive direction is towards the shore. It's 20 meters from the shore to the buoy. And the shore is in the positive direction from 0. So what's the numeric label for the shore? It's in the positive direction from the 0, even though it's in the direction we often associate with negative. So in this case, that's going to be positive 20. I know that can be super tricky when but that's sort of, understanding that is kind of the key to this exercise. The way you just want to think about it is you're starting at 0, and then anything in the positive direction from there is going to be positive numbers based on those distances, and anything in the negative direction is going to be labeled with negative numbers. The raft is 15 meters in the negative direction, so what's the label going to be at the raft? Negative 15. Because this is the negative direction. And so now what happens with this motion, even though the motion is the same, numerically what happens is the swimmer starts at positive 20, swims to minus 15, swims back to 0, and then swims back to minus 15 again. For the distance, yeah. Yep. So to put a position versus time graph, so here's the position. The times, again, that we care about are going to be 60 seconds, 80 seconds, and 110 seconds. And this time, the position labels that we need are positive 20 and negative 15. So the swimmer starts at positive 20. After 60 seconds, the swimmer is at negative 15. After another 20 seconds, the swimmer is at 0. And then after 30 more seconds, the swimmer's gone back to minus 15. And so this motion looks something like that. Anybody have any questions right now about how to do those? I actually already on D2L said that there are a couple of problems that you can work on that are like this kind of problem. Two things to notice about this. The first one is look at the shape of this graph compared to the shape of this graph. All they are is flipped. It's like you took one and flipped it upside down. That came from changing the direction of the positive direction. So changing the positive direction flips the graph upside down. And then notice that the other thing that happened is, besides being flipped upside down, you get a shift. We got a shift vertically. This one started at 0. This one started at plus 20. That happened because we changed where the 0 position was. So changing the 0 position shifts the graph vertically. Okay, here's a bonus question. This didn't come up in this example, but what would happen that would make the graph shift horizontally? Zero time, yep. So if you change the instant that corresponds to 0 time, you get a horizontal shift of the graph. Anyone have any questions about that?
Do you ever graph where the 0 position is? Or the 0 time? Like either one? Is that on the graph that I just didn't see you draw it?
The line only represents where the object is that you're tracking.
Okay.
So you never draw a line to that specifically unless the object is there.
Okay. Thank you.
Mm-hmm. Okay, so the next stuff we're going to talk about, I think maybe I'll pretty much stop there, but let me just introduce what we're doing next. So now, based on these definitions of position and displacement, we're going to define velocity, and then after that we're going to define acceleration. So the next thing we'll do is velocity, and I'll also talk about speed briefly, but speed isn't going to be something we're going to care about. Velocity is. And I'm going to break velocity up into, I'm going to do it in 2 steps. I'm going to first talk about average velocity. And then I'm going to use the idea of average velocity to talk about instantaneous velocity. Average velocity, even though it's the first thing I'm going to introduce, is not going to be important to us. The only reason that I'm introducing it at all is because it'll help explain what instantaneous velocity is. So this won't really be important in this class once we've defined instantaneous velocity. This one is going to be the one that's going to be important to us as we go on. Okay, I'll do that next time.